Hey guys, in this video we're going to talk about Chapter 12, Section 3, Contour Diagrams. Okay, so we've already talked about some methods in which we can visualize surface with cross sections. We're going to talk about another method that we can use today, and that's called a contour diagram. So to visualize complicated surfaces, we can use a contour diagram on which points of constant elevation are joined to form contour lines. So I'm going to be using these two terms interchangeably, contour lines and level curves. Okay, so basically what that means is anything that is on one of these circles in this diagram here has the same height. Okay, and we can see that because, we have this mountain range down here, right? And so this up here, this right here, is our contour diagram. And it's basically telling us what the elevation at each point is. Okay? So like anything that, for instance, is on this, let me do this, and actually let me go ahead and color code. So color code. So this whole thing is our diagram in orange. This is our contour diagram. And the circles that are spread out are the contour lines or the level curves. So this is our contour diagram, the collection of the curves or the circles. And so, for example, one of these circles is at elevation 20, noted by the 20 right there. And so I can kind of just sketch around it. This is a level curve or a contour line, means the same thing. Contour line at height 20. So that means that anything that lies on this curve is at a height of 20, okay? And we can see the projections here. So like this guy right here on the mountain, if we project this guy upwards, we can see that he lies on the 20 curve, as well as let's see, as well as this guy right here. This guy lies on the 20 curve. And so what this is saying is that these 2 points on opposite sides of the mountain are at the same exact elevation. Okay, so we're going to use these to basically, we're going to use contour diagrams to basically project this into 3 space. We're going to take a 2D diagram and we're going to use it to visualize a 3D space. Okay, so the contours of a function, this is the same thing. Maybe I should actually write this in the same way. This is the contour lines. These are the circles. So the contour lines of a function of 2 variables are the curves with equations f of x, comma y equals k, where k is a constant. Basically, the way you can think about this is if you have a surface, such as this one represented in this picture, if you take planes of z equals 1, z equals 2, z equals 3, they're going to cut the surface and create an intersection, okay? So create some sort of picture. And so the idea here is, again, I mentioned this idea of projecting upwards. So this right here, you can see this bottom part. This is the contour diagram. This is the collection of the contour lines. Each circle is a contour line. So, for instance, this circle right here, is a contour line. This is a contour line at level 20. You can think of this as z equals 20. So that corresponds to we can see the dashed line. We can just project it up here to z equals 20. And that's going to represent this whole bottom circle right here. This is at z equals 20. And the very top circle right here is indicated by this contour line in the middle. This guy, maybe I'll draw an arrow here just so you guys can see it. This is a contour line at level 45, aka z equals 45. All right, so that's the idea. And you can see that this is a useful tool for determining 3D shapes, if we only have this information to go off of. Now we can use the other methods that we talked about in previous videos to get the actual, because what we know is from this contour diagram, looking at these circles right here, we can see that the radius of the circle is getting smaller as we go up in height. The radius of the circle is getting smaller as we go up in height. This is z equals 20, this is z equals 25, etc., all the way to z equals 45. The circle is going to be the smallest there. So we can get a general idea of the shapes, when planes at z equals 20, z equals 40, z equals 45, when these planes cut these things. And to figure out what the side shapes look like, we can use methods that we discussed in previous videos for getting those cross sections. But that's the idea here. So let's go ahead and do a bunch of examples. Now the first thing we're going to do is we're going to talk about how to find contours algebraically. And all you do is you have the surface in two variables, inputs x and y, output z. And so we have this surface and it has this equation right here. The contour is obtained by slicing the surface horizontally, just like, let me see if I can draw this a little bit better. Let's see. So the contour lines, or the contours, are found by slicing the surface horizontally with a plane. So like if we sliced it like this with this plane, this would be the plane z equals 45, and it would just cut this thing, and it would make an imprint of a circle right here, and that's what we see here at z equals 45. So we're cutting the surface with horizontal planes at z equals k, and we're going to let k vary. So this very top contour is at z equals 45, and this outermost one is at z equals 20. So the plane that would correspond to this would be just this plane that cuts the surface here at z equals 20. And again, I apologize for my drawings not being the most beautiful, but hopefully you guys can see what's going on here with the plane slicing and how slicing an object like this bell-shaped object with a plane is going to create an imprint in 2D. It's going to create a circle like this. So let's go ahead and do some more examples. Find equations for the contours of f of xy equals x squared plus y squared, and then we're going to draw a contour diagram. Okay, so how does this work? Well, the first thing is we have f of xy, and I'm just going to change this to z. Okay, we know that f of xy means the same thing as z. So we have a function of two variables, x squared plus y squared. And the idea here is to let z vary. Okay, so we're cutting this object, whatever this object is, with various planes. So I'm going to go ahead and first we're going to just say, okay, well, I have x squared plus y squared, and it's going to equal some constant k. So we're changing out the variable z for the constant k. And now what I'm going to do is I'm going to take a look at what happens when I start to change k's value. So when k equals 0, this becomes x squared plus y squared equals 0. Okay? When k equals 1, I get x squared plus y squared equals 1. When k equals 2, x squared plus y squared equals 2. When k equals 3, x squared plus y squared equals 3. And finally, when k equals 4, x squared plus y squared is equal to 4. Okay? So these are my contour lines. This, 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 and this. These are my contour lines. Now you can use Desmos to plot this, but what you should be recognizing is that x squared plus y squared equals r squared is a circle centered at the origin, with radius r. Okay? So what we know about this shape is that as the height increases, the radius is increasing, right? And we have circles. So we have something that looks like, this is going to be a super rough sketch, but we have a circle here at k equals 0. And then the radius gets bigger at level 1 when z equals 1. We have something like this. This is k equals 1. At z equals 2 or k equals 2, we have an even bigger one like this. And so this is kind of a rough sketch, right? We have our circles with each of their respective radii. And so this is what we kind of expect the shape to look like when we plug this in GeoGebra, right? And that's just based on our contours. Let's analyze this a little bit more, okay? I wanna really kind of talk about the nitty-gritty here. So based on this information, what we can say we can say something about the contour lines, right? And the radius of each of these. So because the radius is r squared, the radius here is 0. That's pretty clear. We know that in this case r squared equals 1, so the radius is 1. We know in this case r squared equals 2, so the radius is square root of 2, right? Because r squared equals 2, and if we solve for r, square root both sides, r equals square root of 2. All right. Next thing, here r is equal to the square root of 3, and here r is equal to 2, right? Square root of 4 is just 2. So that's what's happening to the radius. Now look how the radius is changing as we go up along the z-axis. Here the radius is changing by 1, right? The radius gets 1 bigger. Here, if we take square root of 2 minus 1, if we take the difference there, this is going up by about 0.41. And here, we're going up by about 0.32. And from root 3 to 2, if we take the difference of those numbers, we're going up by about 0.27. So the radius is not changing at a constant rate as we move up along the z-axis. Let's write that down. So the the radii are getting closer and closer to each other as we move up along the z-axis. Right? The distance between the radii are getting smaller and smaller. So the distance is getting closer and closer to 0. And what does this mean in terms of what the picture looks like? Because the distance between the radii is getting smaller and smaller, what this is telling us is that the function, or the surface, let's actually write this here, the surface gets steeper as we move up and away from the origin. So this is indicated by the contour lines. Getting closer as we move farther away from the origin. Now let's take a look at what this means graphically. And we're going to use both Desmos to look at our contour lines, because our contour lines, we only have X's and Y's. We don't have any kind of Z involved, so we can use Desmos for that. And then we're actually going to plot our surface on GeoGebra to see that our contour lines are telling a story. So here are a few sketches of some contour lines for our diagram. So we can see that all of these are circles centered at the origin. And so this guy right here is at k equals 1. So this is level 1 on the z-axis, just at z equals 1. K equals 2 is the blue, k equals 3, k equals 4, k equals 5, k equals 6, and k equals 7. So you should notice something about the circles in relation to each other. So what you should notice is the following. As we move outwards, the circles get closer together. And what we said that corresponded to in the surface is that the bowl, whatever this bowl looks like, is going to get steeper the farther we climb up on the z-axis. So let me show you what that looks like in GeoGebra. So again, our surface, so these are just the contour lines, but our actual surface in 3 dimensions is z equals x squared plus y squared, right? And we're setting various values of z to constant numbers to see what these cross sections look like. So here is our surface in red. We can see that it's bowl shaped, and I have cut this bowl with the 7 planes that you see in the contour diagram. Now the contour diagram is just going to be what this looks like when you turn it up like this and you look at the cross sections. So you can see that they're going to be circles of various radii, or various radius. So each of these planes cuts the surface at a certain point, and if you look at the very bottom of the bowl and look at the edges and look at the steepness of the edges and compare that to the top is much steeper, right? The top is much steeper than the bottom. And so we have something like this. Here's our surface. Didn't draw that great either. Let's see if I can draw it a little bit better. So there is this is z equals x squared plus y squared. And what I'm talking about when I say steepness, so at the very bottom, this corresponds to this level right here, k equals 1. Then if we move up along the z direction, it's getting steeper and steeper. Getting steeper. Getting steeper and steeper. And so that corresponds to the circles getting closer together as we move up along the z-axis. So let's do another example. Here we have a surface defined by f of xy equals square root of x squared plus y squared. So in other words, we have z equals the square root of x squared plus y squared. And so the first thing that I'm going to do is I'm going to go ahead and take my surface, x squared plus y squared, square root it all, and set it equal to k, because I'm going to let k vary. All right, and so if I isolate just my x squared plus y squared, I can square both sides, right? And if I square both sides, this equation is equivalently x squared plus y squared equals k squared. So this is what I'm working with right here. And now I want to go ahead and set k to various values to check out the contours. What do those look like? Well, if I set k equal to 0, I have x squared plus y squared equals 0 squared, which is just 0. K equals 1, I get x squared plus y squared is equal to 1 squared, which is 1. When k equals 2, I get x squared plus y squared equals 2 squared, which is 4. When k equals 3, x squared plus y squared equals 3 squared, which is 9. And finally, I'm going to stop at 4. When k equals 4, we get x squared plus y squared equals 4 squared, which is 16. Okay, so what do we notice here about the radius of the circles as we're moving along our contour diagram? Well, here the radius is going to be 0, right? Because, again, this is a circle. We have x squared plus y squared equals r squared. So this is a circle with radius 0. This is a circle with radius 1. This is a circle with radius 2, right? Because r squared has to equal 4. Square root of 4 is 2. Okay. This guy is circle radius 3, and this guy is a circle with radius 4. And so now this is different from the previous example, right? Because look, the radius is going up by a constant amount, namely 1. Right? From 0 to 1, from 1 to 2, from 2 to 3, we're going up by 1. And so what this is telling us is that since this is the same, since the radius is increasing by the same amount, the steepness of our object is the same throughout. So, you know, in this object right here, our steepness varied, right? Because we took these little tangent lines and we just kind of did a little sketch and we said, oh yeah, well, the steepness is going to vary. This corresponds to, you know, the circles getting closer and closer together as we move up. But here our contour diagrams are still circles, but the object's going to look a little bit different, right? The object's going to look a little bit different because the steepness is going to remain the same on the sides. Right? So we have this object like this. And each of these little contour diagrams corresponds to this point right here is just 0. K equals 0. This guy right here could be k equals 1. K equals 2. And so forth. I didn't draw that one great. So the steepness is the same. You can see this on the side, right? If we were to draw tangent lines on the sides, that steepness would stay uniform, right? That steepness would stay uniform. And, you know, you can go ahead and put this in, you can put this in GeoGebra. You can put the contours in Desmos, as I did right here. And in GeoGebra, your surface is going to look just like this, like a cone. And we can see here this is different, right? Because the distance between the circles is uniform. It stays the same, whereas with our first example, the distance between the circles got closer and closer together. Basically, the steepness is changing, right? So for this example, we want to describe the surface with the following contour diagram. Okay, so keep in mind that what this contour diagram is telling us is basically what shape is made with the XY plane as we move along the Z-axis. So right here, this is Z equals 0. And right here, this is Z equals -4. And so the idea here is that the circles are moving closer and closer together as we move down in the Z direction. Okay, so what does that look like? And by the way, the radius of the circle is getting bigger as we move along the Z-axis downwards. Okay, so at Z equals 0, we have a circle that looks like this. At Z equals -4, we have an even bigger circle. Right? And then the circles keep getting bigger and bigger. Now, at Z equals 0, this is just going to be a cross section. So this isn't the bottom of our bowl, right? Because the cross section is 0. Right? If it was the bottom of the bowl at Z equals 0, we would have just a little point right here. And so this guy is going to be Z equals 0. This is happening at Z equals -4. And somewhere is the vertex of the bowl, maybe up there. I'm not sure. We're not given enough information. But if we kind of connect this to make our bowl shape, this is what we're going to get right here. So this is the surface. It's basically an upside down bowl, right? Because we have our Z-axis right here. This is Z equals 0. So, you know, if we were to kind of extend the axis out a little bit like that, it would look something like that. Here's our X, here's our Y. And so this is the point Z equals 0. This, we're not really sure what this is, where the vertex of the bowl is, but let's just say it's at 2. We don't know, because our diagram doesn't give us that information. There's no single point on our diagram. So let's just say it's at Z equals 2. And so to describe this, I would say this is an upside down bowl with its vertex at Z equals 2. Okay, so that's kind of the idea of how we can take this contour diagram and project it into 3 space like that. Okay, sketch a contour diagram for the function with at least 4 labeled contours. Describe in words the contours and how they're spaced. Alright, so we have our function f of xy. That's just Z is x squared plus 2y squared. Okay, so if we go ahead and make some contours, I can start at k equals 0 first. And so remember, I'm just subbing in each of these k's for Z. So when k equals 0, we have 0 equals x squared plus 2y squared. I'm going to just flip it around so that it looks a little bit more standardized. So we have this, k equals 0. When k equals 1, so again, these are our contour lines. Each one of these is a contour line. So for k equals 1, we have x squared plus 2y squared equals 1. K equals 2. X squared plus 2y squared is equal to 2. Okay, so 1, 2, 3, 4, 5 contour lines. And something to keep in mind here, so these are all of the equations you can put in Desmos to make the contour diagram, right? The collection is what is known as the diagram. The individual boxes are the contour lines or the contours. I know it's a lot of new vocabulary, but yeah. So what I want you guys to keep in mind is the general formula for an ellipse. Remember oval. We have x squared over a squared plus y squared over b squared equals 1. Okay? So this kind of looks like that, right? All of these contour lines sort of look like that. And in particular, if we look at the contour line when k equals 1, what we have to start with is x squared over 1 squared plus y squared over 1 over root 2 squared equals 1, right? Because the 2 up top can simply be written as 1 over square root of 2 squared on bottom, right? If I square this guy, I get 1 over the square root of 2 squared is just 2. Y squared over 1 over 2 is the same thing as 2 times y squared. So that's how I went between the two there. And so this is the exact form of the ellipse. What this tells me is that the distance along the x-axis is 2 times a, or 2 times 1, which is 2. And this tells me that the distance along the y-axis is 2 times 1 over root 2, which is approximately, let's see, approximately 1.4. Now let's go ahead and take a look at our contour lines in Desmos. So here are my contour lines, and the collection makes up a contour diagram. And we can see that these are all ovals or ellipses. And, I encourage you guys to put this in Desmos and verify for yourself that this distance right here along the y direction, right, we just looked at this. This distance right here is 2 over the square root of 2, or approximately, what did we say it was? We said it was 1.4. Verify that, and also verify that this distance right here along the x-axis is going to be 2. All right? So that was the ellipse that we looked at. So we can see what's happening when these ellipses move up in the z direction. The radius is getting larger and larger and larger. However, we can see that the distance between the ellipse and the next one as we move out is getting smaller, right? And so this isn't going to be a uniform shape. It's not going to be a cone. It's going to be a bowl shape because of this the spacing that's not uniform. And if we plug our function into GeoGebra, we can see the bowl shape here, and we can see that it's different from the first bowl that we looked at, because if we look at it from the top, we can see that this opening is an ellipse rather than a circle. Alright, so we want to sketch the contours of this function right here for the values k equals -6, 0, 6, and 12. Now, the first thing I want to bring to your attention is what this graph is right here. So we have -3x minus 2y plus 6. I'm just rearranging it so that the constants last. Now, this is a plane, right? Because all we have are x's and y's. We don't have anything squared, we don't have anything cubed, so this is a plane, and we have a constant. So let's go ahead and look at the contours of this plane. What do you think they're going to look like? What do you think the cross sections are going to look like? Well, it's telling us exactly what K needs to be with our contour lines. But the first thing I'm going to do is I'm going to sub in K in for Z. And I get negative 3x minus 2y plus 6. And I'm recognizing this as a linear function. I know that linear functions have the form y equals mx plus b. So what I want to do to make sense of these contour lines is, the other ones we made sense of because the first one looked like a circle, the second one looked like an ellipse, and we know what those formulas look like, and the third one is going to look like a line, but let's go ahead and put this guy in y equals mx plus b form so we can get the idea. And to do that, I'm just going to move over everything. So if I add 2y to both sides, I get 2y, positive k on the left. I just added 2y to both sides. And now what I'm going to do is I'm going to subtract k from both sides. And finally, I'm going to divide everybody by 2. Okay. So this is my formula right here. This is the formula for my contour lines. Now we can see pretty easily what the slope is, right? The slope in y equals mx plus b is m. So this guy is going to be negative 3 over 2x. And the only thing that's changing as we move in the z direction is the y-intercept. Okay, so let's go ahead and look at these various values of k. So we have negative 6, 0, 6, and 12. So when k is equal to negative 6, we have our line, our contour line is y equals negative 3 over 2x. We're just subbing in k as negative 6. And so when we simplify this, we get negative 3 over 2x plus 6. Okay, so that was for k equals negative 6. We get this one. For k equals 0, I'm going to ask you guys to verify these on your own. I get negative 3 over 2x plus 3. Right, just again subbing in 0 for k right here. For k equals 1, no, for k equals 6, they asked us to do that. We get y equals negative 3 over 2x. And finally, for k equals 12, we get y equals negative minus 3. Okay, so these, so we have 4 contour lines. So let's take a look at the contour lines on Desmos. Now, I want to mention that the contour lines that I've plotted here, the colors do not correspond to the colors that I boxed right here. So just kind of disregard that. There's no connection between those. So I graphed all of these on Desmos, and if we put the surface in GeoGebra and we set each, and if we take z and set that to each of our corresponding k values. So remember what we had k equals 0, k equals negative 6, k equals 6, and k equals 12. If we take z equals each one of those numbers and put it in GeoGebra, what we're going to get is something like this. And so where the blue planes intersect the red plane, which is our surface in this case, that's going to be the contour line, right? So each of these intersections corresponds to a contour line, and these are all parallel lines in the xy plane. We know that they're parallel lines because, we can see it, first of all, on GeoGebra, but also remember that parallel lines have the same slope but different y-intercepts, which we have in each of these 4 cases. Alright, so draw a contour diagram for this guy. Now, we should recognize right off the bat that this is a plane. We just have x's, y's, and constants. No x squareds, no y squareds, nothing like that. So our plane is going to take the form z equals 2x plus 3y plus 1. And I want to do a contour diagram, so I'm just going to start at k equals 0 and go all the way to k equals 4. Now, since I know that my contour lines are actually going to be lines, what I want to do first is get this in y equals mx plus b form. Alright, so the first thing I do when I do that is I'm going to sub in k for z because that's the substitution I'm making over here. I'm going to say that k is equal to 2x plus 3y plus 1, and now I'm going to isolate y by itself so that we're in mx plus b form. So I'm going to just subtract 1 over and subtract a 2x over, and I'm going to get 3y equals, by itself, equals negative 2x, and then we have that positive k minus 1. So I'm just doing simple algebra, manipulating this equation to get y by itself. Now I can divide everybody by 3 to give me y equals negative 2 over 3x plus, and then we have our y-intercept, which is k minus 1 over 3. Alright, so now for each of these things, when k equals 0, we plug in 0 for k. When k equals 1, we plug 1 in for k, and we get our corresponding lines. So I'm going to ask you to verify this on your own, just for time's sake. So when k equals 0, when I plug that 0 into this equation right here, what I'm going to get is y equals negative 2 over 3x minus 1 over 3. When k equals 1, I get y equals negative 2 over 3x. When k equals 2, I get y equals negative 2 over 3x plus 1 over 3. K equals 3, I get y equals negative 2 over 3x plus 2 over 3. And I'm actually going to leave the k equals 4 out. We don't need that many. So what we can see here is that our contour lines all have the same slope, but different y-intercepts, right? And what that means is that we're going to have parallel lines in the xy plane. So this, again, this collection of lines is our contour diagram. And you guys can plot each of these in Desmos to see what it looks like, and then go ahead and plug this guy into GeoGebra, and then you can see that the intersections of the planes z equals 0, z equals 1, z equals 2, z equals 3 is going to correspond with each of these contour lines here. Alright, so those are our contour lines here. And the diagram you can draw by just putting each of these lines into Desmos, such as we have here. So this is our contour diagram, and this is our plane in GeoGebra. I encourage you to look at each of these intersections. So the first one we said was z equals 0, or k equals 0, z equals 1, z equals 2, and z equals 3, and check out those intersections and verify that they correspond to each one of these lines that we have here. Alright, sketch the contour diagram for z equals x squared minus y squared. Alright, so I've already done this for you guys in Desmos. Here are our contour lines, and what we can see is that this is making a hyperbola kind of shape. And so if we put this in GeoGebra to kind of see where where these shapes are coming from. Let me delete all of this. Let's delete this too. Oops, I didn't want to do that. I wanted to delete it. Okay. So we have z equals x squared minus y squared. Alright, so this is our picture. Oops. And we can kind of rotate it around, and we can see that if we're looking at this thing from above, you know, we have our xy plane in the usual spot, and we can see that this does indeed correspond to what our contour diagram looks like. So if you were to, you know, slice this thing horizontally with planes, the shape that the plane is going to make with the surface is going to be hyperbolic. All right. Let's do one more example here. So the figure shows the contour diagram. Answer the following questions for the points 0, -1, and 1, 0. So the first thing is we're going to find the distance h from 0, -1 to 1, 0. So basically we can just use the distance formula because we have 2 points, x1, y1, x2, y2. And so our distance formula is going to tell us that we can do x2 minus x1 squared plus y2 minus y1 squared. And so when we simplify this guy, we get 1 plus 1 under the radical, so that's √2. So that's our answer for part A. That's just the distance. Now it says find the change of f, the difference between values of f of xy from 0, -1 to 1, 0. So what does that mean, first of all, values? Basically, we're trying to find the z-coordinate, which is given by these contour lines. So first of all, f of 0, -1, let's figure out what that is first. So we want to see what contour line, when x is 0 and y is -1, what z is going to be. Alright, so if we look at our axis as our x-axis, so when x is 0, when y is -1, we're right here on this contour line. So this guy, this contour line says, hey, I'm going to have a height of 2. So z is equal to 2 right here. So this is going to be 2. And the other one is f of 1, 0. So again, x is 1, y is 0. And so we look for this on our diagram. So when x is 1, we're right here. When y is 0, we're right here. Okay? So we can see that this guy lies on 2. A height of 2. This is our contour line. And actually, I'm sorry, this should have been -2 up here. So when I find the difference, I just subtract. So the difference, or delta f, is going to be -2 minus 2 is going to give us -4. So that's delta f. And this distance should have actually been called h. I'm going to just relabel it that, since it said find h. Okay, now it says find delta f over h. Now this is pretty easy because we just found delta f right here. That was -4 over h. We found h up here. That was √2. And so our answer here for the average rate of change is -4 over the square root of 2.